The last thing I want to talk about this week is featurization. That is, if we have some data set, how do we figure out how to represent that data set as a feature vector for a classification model in this case? This is a kind of very practical topic that I think maybe we could talk about it almost in any section, but we're going to talk about it here particularly because it has some important implications for linear models. So I'm going to talk about a couple of different considerations one has to make when it comes to featurization. So the first one has to do with this assumption of a linear model and a linear decision boundary. So let's look at a case like this, where here's our features. We're in a 2D space. That is, we have two features, x1 and x2, and the label is indicated by the color black for 1, white for 0. So one big downside of linear classification algorithms like linear discriminant analysis and logistic regression is that they can only ever give you a linear decision boundary in our feature space, as we talked about. So notice that there's no way we're going to get a good linear decision boundary on this feature space. Like maybe the best we do is like this or something, and still that gives us really terrible classification accuracy because there's all these points that we've classified incorrectly. However, that linear boundary is in feature space, and we can often get a nonlinear classification. Often it's very practical to do classification using a linear model like logistic regression and get a nonlinear boundary by pre-processing our features. That is, finding some other representation. So now I'm showing the same points, but instead of putting x1 and x2 on the horizontal and vertical axes, I'm putting x1 squared and x2 squared. So it's not too hard to see that these points now here I've just put into this new space, and now it's easy to see that there is in fact a linear boundary that separates those points. So that is to say that often the best strategy for classification, even when we know that our decision boundary won't be a linear hyperplane in our initial data space, is instead to pre-process our features to add some additional power to our classifier. So some common ways to do that. The first is to add polynomial terms. For example, put x1 squared, x1 to the 3. Put each of those in our feature vector. That will, of course, if we're using a linear classifier like logistic regression, it's going to give us more parameters to learn, because if we've gone up to power 3, that's increased the number of features, the features that the model is going to learn, or the number of weights the model is going to learn by a factor of 3. But it perhaps lets us learn more complicated nonlinear functions in our original feature space. This one being an example. Another one is cross terms. That is, we can put x1 times x2, x1 times x3, x2 times x3, and so on. We can put those in our feature vector as well. Again, that can give our linear classifier some additional power. Let's look at a couple of other common featurization strategies. We just looked at polynomial features and feature crosses. Another one that comes up often in practice is a one-hot encoding. That we use when we have a feature that's a discrete value. Let's say I can take 1, 2, 3, or 4. That won't work well in, for example, logistic regression if, let's say, these numbers don't have any kind of order to them, because the model is looking for a linear boundary in feature space. So, for example, there's no boundary in X that divides. Let's say our label is 1 if X is 1 or 4, and not if it's 2 or 3. There's no way a logistic regression can give that decision boundary. So we can switch that to one hot encoding by splitting into 4 variables, x1, which equals the indicator of x equals 1, x2, which is the same thing, but for x equals 2, and so on. Another featurization strategy that comes up specifically when dealing with text is, well, how do I represent a English sentence as a feature vector? Maybe I could do it as, one feature per letter in the sentence, where spaces are their own thing. Well, that has a couple of problems. One is, how do I deal with a different length of sentences or documents? I could put some padding, but this is all getting very complicated. And in fact, that tends to work very poorly in practice. Something that works much better is maybe we use a bag of words featurization, which is that instead of what I just said, instead I have a vector with one feature per word in English language. So I end up with a couple thousand features, and the value of that feature is the number of instances of that word in that document. There are some more principled ways to do that. One example is TF-IDF. I'm not going to say what that is, but it involves doing some normalization on that bag of words featurization I just said to account for the length of the document and the prevalence of a given word in the English language, and so on. So this is just a very short introduction. The thing I want you to think about, though, is that the choice of features to represent a given data set is often just as important, if not more important, in practice than the actual model you generate using those features.